யாருமே இல்லை. வெளிச்சமே இல்லை. நீங்க பிரைட்னஸ் கொடுங்க. பிரைட்னஸ் ரொம்ப ரொம்ப இதா இருக்கு. செட்டிங்ஸ்ல போயிட்டு எக்ஸ்போஷர் தான் இதானே? அதான். ஓகே. ஓகே. என்ன கொஞ்சம் கேளுங்க. இல்ல கொஞ்சம் அரைக்கிறது. ஓகே. அங்க வேண்டியங்க இல்ல பிரபாரணனை கிடைக்குன்னா இப்ப மேல என்ன கொஞ்சம் இது வரைக்கும் ஒரு ஆள் கூட இல்லை. நானும் லைக் போடுறேன். லைக் யாரும் லைக் பார்க்க பண்ண முடியாது.
அந்த லிங்க் அனுப்பி விட்ருவோம். குரூப்ல யாராவது தான் ஜாயின் பண்ணுவாங்க.
லிங்க் எப்படி அனுப்பணும்?
லிங்க் அனுப்பினா எல்லாம் வந்து பார்ப்பாங்க. மேலே இருக்கிற அந்த லிங்க் தான்
யாரோட பார்ப்பேன். நான் பார்ப்பல.
இங்கே இருக்கவங்க பார்க்க வேண்டியது.
யூடியூப்ல வந்துருச்சு ஆல்ரெடி. லைவ் வந்துருச்சு. IEEEOES-Guest-Lecture டாக்டர் ஃபிரான்சிஸ்கோ
லிங்க் அனுப்பி எனக்கு அனுப்பு.
இது எதுல அனுப்ப? மேவலாப் குரூப் போட்டுமா? மேவலாப் குரூப் போடு. Matlab at DOE.Tabilas.
லிங்க் எடுத்து
வாட்ஸ்அப் DOE ஸ்பெல்லிங் கரெக்ட்டா Matlab at Tabilas.DOE.IEEE.
No.
சாம Facebook டிபி ரெடி பண்ணி வச்சா
கொடுங்க.
Mav_Abhilash.
எல்லாமே மறந்து விட்டாரு. Mav_Abhilash@DOE.IEEE சொல்லிட்டா. அந்த கலர் வரல, சிம்பிள் வரல. நீங்க தப்பா சொல்றீங்க கேட்டா. Mav_Abhilash கரெக்டா தான் இருக்கு. Mav_Abhilash கரெக்டா. Mav_Abhilash வந்து IC உங்க சொல்லுங்க. IC ஸ்ரீதர்
38134.
ஸ்ரீதருக்கு போட்டாச்சா? டைமேலா அவ்வளோதான். நான் அனுப்பிடுவேன். நான் இப்போ கண்டிப்பாக நீங்கள் அதில் போட குரூப்லாம் போகிறேன். எதுக்கு 2 நம்மளுக்கு தெரியுதா? பேசு. ஹலோ. அதான் சவுண்டு அண்ணா ஸ்பீக்கர் வச்சா கண்டிப்பா எடுத்துக்கணும். ஸ்பீக்கர் வச்சா ஸ்பீக்கர்ல தான் பேசுவாங்க. யாரே லைவ்ல இருக்கவங்கள நீங்க போன்ல நீங்க மேவ் லிங்க் அனுப்பிடுங்க. மேவலாப்ல போட்டுருக்கேன். இன்னும் நான் வரலன்னு சொல்றீங்க. இல்ல இது இமெயில் எதுக்கு அதை பார்க்கணும்?
யூஸ் வரணுங்கிறத
யா நான் பேசுங்க.
Good afternoon, everyone.
நல்லா என்ன அது இங்க வரணும், இங்க வந்து கேட்கணும்.
Good afternoon, everyone. We'll start our lecture soon.
அண்ணா வெளியே போயிட்டு கேட்க தான் கேட்டவங்க.
எதுவும் பேசாது, இந்த வண்டியை தான்
நான் இங்க இருந்து போயிடுறேன், இங்க இருந்து போயிடுறேன். இல்ல அங்க ரைட் கொஞ்சம் சூம். இப்ப கேட்கறேன்.
இப்போ மயக்க
It's fine. You just take connection. Your voice will go into sleep. Oh, I really took it.
Okay.
Hello, everyone. Good afternoon, everyone. So it gives me great pleasure to introduce our speaker for our IEEE OES talk here, Dr. Francesco Maurelli. Dr. Francesco Maurelli is a professor in Marine Science Systems and Robotics at Constructor University, formerly Jacobs University in Bremen, Germany. where he also serves as a program chair for Robotics and Intelligent Systems program. He obtained his PhD at the Ocean Systems Lab in Edinburgh, Scotland, with a thesis on intelligent localization of autonomous underwater vehicles. He has been the scientific manager at Technical University of Munich, where he led European-wide universities initiatives to support moving robotics technology from lab to the market. After a research stay at MIT as a Marie Curie Fellow, he has accepted a faculty position at Constructor University. His research interests are focused on persistent autonomy for maritime robotics, perception, autonomous navigation, intelligent decision-making, sensor data processing, and fault management. Dr. Maurelli is an executive committee member of the Global Young Academy, co-chair of the Technical Committee in Marine Robotics, and co-chair He's a co-chair of the Young Professional Committee in IEEE Robotics and Automation Society and member of Administrative Committee of IEEE OES.
Okay, thank you very much for the kind introduction. And for me, it's a great honor to share with you a little bit of my experience in this domain. So these are some of my friends. As you can see, some of them are maritime robots and their models, some of them are food tracers, some of them are very different robots. Like this one is more like a design done in collaboration with the European Space Agency about the moon and exploration of the large planets in the moon. Well, we can say that was running before it became so popular. Here, that was in Germany many years ago, when we had to stack a lot of different sensors on top of cars. Well, now everything is much integrated and it's already a reality. So the link to me to IIT Madras are twofold. So from one side, I'm from Bremen in Germany, and there are many links between Germany and IIT Madras. It was one of the IIT that was doing in collaboration with Germany. And in particular, Bremen, there are quite a lot of students coming from IIT Madras to the University of Bremen, to Hochschule Bremen. And some years ago, they organized an alumni meeting from IIT in Bremen. And by chance, they asked me to go and speak. And they had no links to India whatsoever. They were looking for somebody talking a little bit about robotics, AI, technology, how they impacts the work. And that is my first real connection with IIT. Then, of course, we have several more. I've been at the NIO in Goa a couple of years ago with the Metzer, and it was a very nice Marine Robotics school. And with Professor Asma in the Technical Oceanic Engineering Society. So it's kind of closing a circle because I couldn't visit Chennai for the Ocean Conference in 2022 because of the COVID pandemic. So I'm happy that now it's a good occasion to share a little bit of life with you. Share my experience and learn from your enthusiasm and what you are doing. For engineering society having technical problems. I remember when I had to do my presentation for my master's thesis in computer engineering. In Santiago, it's the biggest European university. A huge room with all master theses and they have a public presentation. And nobody managed to get a project for a long time. The room full of engineers.
How many engineers does it take to make a project for work?
Exactly. No, but this is but that's fine. Yeah, perfect. Well, a few things about myself. That's the introduction was already complete, but I still like to show this slide mostly for this logo on the bottom. Now, this logo on the bottom is not to say I'm active, but it's actually an invitation for you to be active in this professional society. Why is that? Because alone we can do that. Especially if we want to address big engineering problems, we cannot do things alone. That's why we have this organization. The goal is to bring people together from different countries, from the same countries, from local sections, from different disciplines in some cases, and to make them working together. So every employee is an umbrella organization for these are two logos. One is the Professional Society, Oceanic Engineering Society. Without them, we wouldn't have the main conferences. We can publish, we can network, we wouldn't have the main journals, we wouldn't have summer schools. And on the left-hand side, we have Global Academy, that is a science academy for young scientists worldwide. So India, for example, has the Indian Science Academy, but it's also Indian, so there is the Indian Young Academy of Science. The Science Academy for Young Scientists. And many countries, Germany is the same. So both England has the German Science Academy, and then there's the UK Academy as the German Young Academy. And GYA was born in order to have a science academy for early career researchers that will be worthwhile. The membership is capped at 100 only, and it's only for 5 years, because we cannot be young forever. So it's also a way for the organization to get developed in them. That's something that some of you might be interested in. The previous co-chair, the last co-chair of the GYA was actually from India. And that's why I visited India in June, because the Global Academy Conference was at IIT Hyderabad last June. So some of you may think about applying for membership next year, in 2 years' time, whatever. And you may ask where I'm from. Why is it Constructor University? What is it? Well, it's a private English-speaking university in Germany. So I will spend a couple of words to present the university first before diving into some of the specific aspects. Now we are campus-based. That is very rare in Europe. So in Europe, usually it's a university building where you can have labs, you have lecture halls, and so on. Now we have our students living on campus as well. That's more normal for you. We are university, we are campus, so not much. And it's very, very useful to have a private university in Germany that is English-speaking and is research-oriented. So in most cases, a private university can be just a business school or an IT diploma mill. But actually, what we do is we do research on many different topics, many different aspects. So we have, this is additional practice. And here is my office. So if you come to visit me, you can find me around here in my office, or you can find me around here, that is our water lab, where we have one of our Marine Robotics, or you can find me here, where we have robotic arms, we have small robots, and non-community, several peppers, several now robots, humanoid robots, we start human robotic production. Or you can find me here, where we have a small autonomous driving lab with a small castle where we teach autonomous driving to our students. And on the left hand side, there is not the picture, we have 4 biologists for students. And faculty also each usually for large same quality students. We have 3 main schools. So School of Computer Science and Engineering, where I'm from, Robotics. School of Science, School of Business, Social and Decision Sciences. In Computer Science and Engineering, we have Computer Science, Computer and Electrical Engineering, Robotics and Intelligent Systems. On the master's level, we have Data Engineering, Computer Science and Software Engineering, and Data Science for Society and Business. In the School of Science, we have everything ranging from cell biology to chemistry and biotechnology, medicinal chemistry, health and environmental sciences, physics, quite all the kind of natural science part. And in the business software and decision sciences school, we have business, industrial engineering, global economics, management, international relations, arts, politics, history. So as you see, it's very, very broad. At the same time, it's a relatively small university. We have only about 2,000 students, and that is by constructor because the space is limited. Also, we want to have enough space for the students to move around. We've got to build a new student accommodation place in the near future. We have signed an agreement with the construction company to start the campus. And one of the great things I really like is the international idea of the university. Actually, the first name was International University of Bremen. It was a project from the city of Bremen to revitalize this area. That it was, at the time, it was an old military barracks, and it was not used by the army for a long time. So it's also a very powerful message that we can do the educational institution in a place where it was an army barracks. And the idea was really to provide world-class education, English speaking, in the hubs of the European Union and in the hub of Schengen. Schengen is an area that is not exactly European Union, almost, where there is freedom of movement, freedom of work, freedom of goods and services, commerce, The university is not only a university, but it's actually in the general being a constructor ecosystem. So constructor is a relatively new name. Only a couple of years ago we changed name. And then we changed name because the Jacobs Foundation, which was Canadian University before, said back then, and the investment process. The constructor group came in. It wasn't called constructor group at the time. And then they also changed name after investing in the university. And it's very interesting. It's the general idea behind this education is a solution to all levels. And I think it's a very powerful message. And by education, of course, the university plays a central role, but it's not only university, but it's what happens before the university. That is why we have constructor knowledge that is there in school, on preparatory summer school, preparatory activities for young kids. And then learning and education is also what happens after the university. Why we are in the process of setting up degrees, certificate courses, and so on. But then it's also a reinforcement with the industrial aspects, partners, and capital. Like a small town with all the different aspects from the kids growing up, so school, education, and work. And in particular, all the aspects of construction technology are dealing in particular with either intelligent systems, so we have an autonomous racing car and an autonomous racing team in collaboration with Constructor University. There is a Formula One style car that participates in competitions like Formula One. And so we managed to get very good positions. So sometimes we won, last time we got second place. Very, very interesting work. There was Abu Dhabi last time. And the other aspect is EdTech. So we are developing together with startup tech software for education. So technology used for education. That range from LMS system to AI-based proctoring systems. We are even toying with the idea of having avatars for the professors, so that every professor can have its own avatar, and you can have you can choose the angry mode or you can choose the happy mode or the sad mode, and so on. So this is my team currently. And there is a slide I always like to pass because, as I said from the beginning, there is not much we can be done alone. So I know the person working with me, and I have several different PhD students. And the interesting things you see was on the side, they all are funded by very different sources. So we have PhD students financed by industrial company like Airbus. We have PhD students that came in the DLE sandwich program from India, actually. So Asmati came from CSIR Siri Ghani. She came to us for the mission was 1 year, and she extended for a second year, and she's now back in Ghani. So the carbon from Pakistan was also some DLE scholarship in the project we had from Germany and Pakistan that DLE was sponsoring. Shishing from China, Science Scholarship Council. We see a German science foundation. So it's the game of the event is similar all around the world. We always have to look for money to support our team, to increase our team, and to get everybody playing with enough material, enough having the right infrastructures around. And of course, Michael that recently joined us and Martin that is with us having some time. They are really fundamental in helping out with setting up all the infrastructure. Our main research is in autonomy. And I apply for many different domains, of course, in particular, the marine domain. My main research activities has been always in the water since 2007 until now. And autonomy, of course, is a very general word. What does it mean? Well, it's a lot of different things. So here I just got some of the others, like sensor data processing, sonar video later, and what we do, the navigation, localization, SLAM. Then it's about faults. Nowadays, robots that have faults, they just stay there, or they just continue to do whatever they are doing without really understanding that it's a problem. So understanding that it's a problem, understanding how to solve the problem, is actually showing a high degree of autonomy. Then there is a representation that is kind of helping all the other aspects. Yes. And making them. Now this is a picture that shows the fluid cycle between sensing and perception and actuation. There is something that we do as humans all the time. Now let's see, for example, from the sensors, like our eyes or here, sometimes tactile. Well, we do the same observation, and then we have some idea about where we are in the space. For example, here, I'm not doing consciously, but all the time when I'm working, I'm checking, oh, am I going too far? Maybe I should stop it because I shouldn't fall from here. There are a lot of things that we do all the time. We are linking our actions to our perception. And in this case, the belief is not anything to do with the religion, but it's about the belief of the robot, so where the robot is in the world, or how the robot appears in the world. And then we can do our planning aspects, moving to the control, so telling the legs to move forward, and then the legs will actually move, and then actually again, and then do all this process all over again. Now there is a shortcut here, because not all the time we have to think about a long plan. So if I just need to go to the door, the plan is a terminal or straight, and then I just execute this plan. So from the perception, so from seeing where is the door, I can immediately give commands to my legs on moving towards the door. If I go to the door and the door is closed, then I need to do some planning, and I have to think about, okay, the door is closed, so what do I do in order to exit? Because the current plan is invalid, so I need to make a new plan, and that is why we do a new plan, and then we execute the control again. Now, in all this, why Marine Robotics? Well, you are from the School of Naval Architecture, so Oceanic Engineering, so you know better than me. Two-thirds of the planet are covered in the water. So this is something that is just a factor. And we know so little about these two-thirds of the planet. We know a little bit about the cost of life. But as long as we want to go a little bit deeper and more further, then it can be more. I mentioned the project with the European Space Agency about the moon. So I've seen maps of the moon. We were looking about the minor speeds and landing areas, then potentially moving a rover over the moon and going down. And from here, we have such detailed information about the moon. In comparison, we know nothing about the oceans. So the map that we have about the depth of the oceans are so shitty in comparison to the maps we have about the moon that is way far away from us. And the ocean is our planet. And it's not only our planet, it's our life. So about half of the oxygen that is needed for humans comes from the oceans. So sometimes I ask people in the audience, okay, they do breathe, and then they say your second breath actually came from the oceans. Do you know that? And that shows that even landlocked countries like Switzerland, for example, they are all affected by the health of the oceans. And healthy oceans means healthy civilization. If the oceans is dying, you might need to as well. And then we do have a lot of resources. So the oil and gas, wind farms, shipping aspects. I think that around 90% or even more of the shipping worldwide by volume is done by ships and not by air. So, as we always that humanity has been always flourishing close to water. So if you look around ancient civilization, where is the house? Well, usually on the seaside or a river, here are all those reasons. Nowadays, also geopolitical situation makes the water a very vital area. Many of the wars are actually happening in the water, not in the land. Even the Ukrainian war, there is a lot of things happening in the water, way more than we get. So having a good aspects of understanding how robotics can support also protection of critical infrastructure, security, harbor security, or shipment inspection. There could be potential threats in bombs on the ship hull, or how to find potential threats seabed. So these are all topics which are unfortunately very, very relevant. So these are the typical ROVs, big industrial robots that people can use in order to inspect the subsea domain. Not only to inspect, but very often they have manipulators and they can operate on Mars. This is pretty normal in the oil and gas industry. They have several of these. Or you can collect rocks, also pretty popular, but mostly in marine geology, marine biology. You try to examples of different things which are in the water. Now, Bremen is a great place for marine robotics, not only because of our university, but also we have Maurelli, that is the German Center for Maritime Research, and they have several of these big papers. This is great, but it's it requires a control loop, which is done with a cable, with a tender management system, and then we have a human pilot usually in a container, and a big ship playing a very expensive video game, because the cable is connected to the vehicle. You can see what the vehicle sees, and then the joystick similar to play PlayStation, but it's slightly more expensive. That is fantastic from a engineering perspective, but it's also very costly. So even if it is fantastic, we can do things which are even more fantastic. Why is that? Well, a good thing is that we have a human in the loop, of course, we trust humans. The fact that this cable allows us to give energy to the robots. If you don't have energy, then the life of operation is limited. And most important is the communication aspect. We are all communicating with WhatsApp, with Wi-Fi, but all these things don't work underwater. They might work sometimes on surface, not always. But underwater, all these things are not there. So you don't have GPS, you don't have Wi-Fi. So in order to communicate, if you have a cable, then of course you can transmit data and high quality and so on. If you don't have a cable, well, too better. If you don't have a cable, we have to resort to acoustic, the bandwidth is very limited. Or optical, there are some optical modems which also page in very crystal water. Of course, as soon as the water starts to become turbid, the visibility decreases and the range decreases. So with acoustic, you can communicate with pretty much any water conditions up to kilometers without problems for depending on bandwidth, depending on frequency. With optical modems, because it's lights, not only visible lights, but essentially electromagnetic waves. It's in the range of meters. So I say, okay, for example, to offload data. You can have a nice underwater robot that swim around, collect a lot of data, and then goes closer to a docking station. It doesn't really dock, but then it has a nice position control, and then try to offload the data to the optical model. So this is possible. And if you want to have two robots communicating with each other in a multi-way condition, then optical model is optical. Now, the fact that the human is in the loop and the human decides is something that many companies like, because many companies are scared about robots taking their own decisions. But very often, it is also a disadvantage, because humans are great, but are not so great. I mean, our computational capacity is not as good as the one from computers, from the robots. So if we think about all forces, all currents, the robot that is maybe 2 kilometers of distance, they can sense all the currents, they can have first feedback about all the forces, they can compute everything, they can take better informed decisions than us very far from the place with our great brain, but also limited. The key aspects, negative aspects actually of using these vehicles is that they need a vessel to support them, especially if they are big. And the vessel is very costly. So we are talking about tens of thousands of dollars per hour. And it's not only the cost of the petrol for the vessel, but it's the cost of all the fuel, because you have a lot of people on the vessel. And then if you want to operate a robot, so all the other people don't have anything to do, so they are there not doing anything. So you have maybe 20 people who are sitting until you finish your work, and then the ship can move so that the other people can do the other things they want to do. So the cost is very high. And the operation is also very clumsy because you need to have a big ship that is there and stationary and not doing anything else. There are also other aspects where cables cannot really help. So we cannot go with the cable to explore wherever we want to. We cannot explore on the rise with the cable, because the cable will get stuck, and the robot either is lost or it's not, or it's not free to move around. So cutting the cable could have great economic advantages and could have great unlocking opportunities of going to places where we cannot go easily. And that is why we get to this idea of persistent autonomy, not just autonomy, but some people think autonomy is a big battery, that my robot is autonomous. Well, in the field, autonomy is not just a big battery. Autonomy means you understand the environment, you understand the changes in the environment, and you are able to determine your plan dynamically. So it's not that you write a mission and the robot just executes your script, because there may be changing condition. It's like I say, I go to the door, but the door is closed. Well, I don't want to get stuck. I want to be able to plan and with a different door. Able to recover from errors in task execution is also very important. All these aspects about faults, from component fault up to logical faults in the mission planning aspects. Like you are handling a valve that actually is the wrong valve you're attacking. How do you detect you're doing something wrong? It's still a failure, but it's not a technical failure in the sense it's not a hardware failure, it's not necessarily a software failure with a model crash, but it's still a failure at a mission level. So how can we do this? And well, I think that's, if you think about humans, how do we do that? So we say, well, we have our brain. Yeah? Our brain is great. What does it do, our brain? First of all, is storing a lot of information. So that is why we just passed a block here that is knowledge base. So you cannot have any informed decision if you don't have information by definition. So when we go to politicians and we told them, well, you need to make policies which are science-based, well, that means based on something. So the same, if you tell to the robot you need to take informed decision, well, there needs to be something where the robot can get information. And the same way we do our memory and our way of storing information in our brain is also very particular. So sometimes you don't remember anything about something, and then you just get a cue, and from that cue you get everything. And you remember everything that happened 20 years ago. So ways to organize the knowledge in the robot so is also a crucial factor that enables autonomy. But how do we fit this knowledge base? Again, let's think about ourselves. We have our brain, we remember our groups, we remember our people, we remember our parents, our friends, we remember what we like to eat. How is that? Is that because we first saw these people, we experienced this with our sensors. So we remember our taste of this food with respect to the other food. When we touch different surfaces, we understand or we remember that this surface is actually quite nice, this actually is very rough surface. So we store information in our brain based on our observations. So this is a block which are called external. So external means all the aspects about the world that we can perceive as humans with our eyes, our ear, our tactiles. In the robot, it will be similar. We have cameras, in the way we have sonar, we could have altimeter, depth sensors, we could have lidars, underwater lidars. So all this information that brings us information, all these sensors that bring us information about the environment. But if you think about our brain, we don't have only information about the environment. We also have information about ourselves. We know that sometimes high leg is hard. Yeah? So we also have information about internal aspects. So we are able to connect our eyes to things. We know that we know the spatial dimensions. So if you close your eye and ask you to touch your left hand on your right eye, you are able to do it because you have a special condition of your body. So you have a lot of information about your body, how it functions, so what it works, what it doesn't work, and you use this in order to plan as well. So you need to go to a certain place, and if you are late, you decide to run, and because you know that you can run. So you know that you can do specific actions. Or you decide to work because you know that you can work, you can time. So you store information in your brain also about your capabilities and your components to some extent, because you know that if something is happening, then you start working in a different way because, well, I have to keep working here, so I just start working in a different way to readapt to the failure to some extent, to the fact that I had a problem on the field. And all these things is something that we need to try to do problem. So, well, all this is information, of course, it's dynamic, come in and out, but we also need to be aspects on planning aspects, of course. All the aspects that say, okay, this is my mission, this is my reality, this is what I can do. Now, what I should do. So, what are the sequence of actions that I'm going to do? Now, these numbers are organized in this way because they are on top of a diagram that is here. And maybe we can see it without the notes. So, now, it's the same diagram, but a little bit more in detail. So, here we have what we call the ontological knowledge base, where we have information about the environment and about ourselves. We have the external subsystem, we have a bunch of different sensors, camera, LiDAR, pressure. We have some ADR, autonomous target recognition. Then we want some stack information. So you go from a signal process, signal aspects into a symbolic aspect. So you can find information about the world inside the environment, inside our ecological environment. Then about the internal aspects. Now what we see here is a specific part about thrusters. So thrusters is a kind of a key component for a robot. Because if you don't have thrusters, you cannot move. So this is part of the actuation. So we work on thruster training. And we had a thruster diagnostic system that was based on energy reading. What we were doing, we were measuring the energy consumption of each thruster, and we were comparing this with our model. So if you were consuming way less energy, that means that the thruster was not really firing working, so it was probably a problem. If you were consuming much more energy, probably there was something wrong with the mechanism, something was broken, it was sucking out energy. And then we had the fault mitigation aspects. What we have inside the base is what we call the link between the components, the capabilities, and the goals. So I said before, if I'm late, I decide to run. If I'm not late, I'll just walk. Or if it's very far, I don't want to work 3 hours, so I just take a car, or I decide to cycle. So you know that you have a lot of different capabilities. So you have different components. You have your legs, you have the bike, you have the motorbike, you have the car. And you know that with the legs you can walk and you can run. With the bike you can cycle. With the car you can drive. The action, for example, is reaching building 101. Now you can do this action using this graph in different ways. So you can try to reach to fulfill specific actions using different components on our level. So what does it mean? Let's say, for example, I work, and then I start working, I decide to let's work reaching building. Then I see that it's late. The fact that it's late passes me an additional constraint, but they actually see the same. I still want to reach the building, but I want to reach it in a different way. So instead of using the walking, I start using the running, for example. Or I'm too tired, so my legs don't sustain me anymore, or I am making a failure. So this part cannot be used anymore. That doesn't mean that I cannot achieve the goal. So even if you have a failure, you might still be able to achieve the goal, but you need to use a different route. So this is an aspect more on the symbolic level on how do we use tools. So we need the lower level aspects will be the thruster failure. I will show you later on some more information on how to adapt thruster allocation metrics to failure, but also on how to rearrange your plan completely using different components than your original selected. Now, the plan here is also really important information because if your mission is to inspect all the pillars, so if you're expecting a bridge, At the beginning, maybe your map is empty, you don't have anything in your map, then you start seeing something, then you add information to the map. Then either is something that the plan is interested in, so it has notified, hey, there is a villa, and then the plan to decide, well, then we stop the general inspection, kind of normal inspection area, and we decide, let's go and have a closer inspection to the pillar before we continue to our local. So we insert a curve fragment inside our general plan in order to be opportunistic. That's the opportunity. If you see something of interest, let's take the task and then let's continue our general. Now, some examples. I want to show you some examples of this subsystem. So from sensor into data. Actually, it's another aspect here about new advantages that is sometimes you need to take a decision in order to understand something. So if you see a person from the detector, sometimes you do understand who the person is. But I bet that sometimes at least with one of you, it might happen that you call somebody a decision on the back, the person comes and it's actually a completely different person. So if you want to understand the environment, sometimes one view is not enough. So you see one view, and then you say, well, from this view, it could be object A, but it could also be object B, I'm not really sure. But if one of these objects is actually relevant for my mission, I need to insert specific viewpoints dynamically, because I need to understand if this is an object of interest or this is not an object of interest. Think about micro-intervention. You do want to localize all the lines in the sequence, for example. So if you see something and say, well, this could be a line, but could also not be a line, so maybe let's have a different viewpoints, a different angle, different rate, so you get a better understanding of the environment. So we show you now some aspects about this blocks here, so sensor data processing, essentially, the visual and the sonar. And I will explain you a little bit about our work a little bit on fault management. So on vision, so these are two different work. So the one on the left was to inspect underwater infrastructure. So it was a kind of a crossover with civil engineering because very often, actually regularly, owners of infrastructures in the water need to inspect them to check if there are potential cracks, potential damages. So that applies to dams, applies to bridges, applies to harbor walls. And we did this work was specifically on visual data, and we try to automatically detect cracks. As you can see, it's not only the crack, you have just a white wall, but there are a lot of small other things because the environment is dynamic in the water. There is always like cooling happening in algae. We're discussing about the algae in the pool area of the lake, for example. The image on the right is quite different. It's also very different also. And we are in Sicily, in South Italy. So this is off the coast of the island called Vulcano. And surprise, surprise, the island is called Vulcano because it's a volcano. Now there is a volcano and it's very active, actually. It doesn't erupt, but there is a lot of volcanic activity. So if you go there, there is constant smoke around there. And some of these volcanic activities actually happening in the water. So we see a lot of bubbles coming up, or these other kind of vents coming from the volcanic activities. And we wanted to do a study to actually measure how many bubbles, how much gas is actually released. And then we connected this into pH maps of the area in different years. We used to go there every year taking measurements. So we could do a change detection and analysis and inform the authorities about the health hazards of the activities. So this is a very real problem, real applications. Because the island, for example, has been closed to tourists for a good 6 months because there was increased volcanic activity and they weren't sure if it was safe or not. They even forbidden everybody to sleep in their place apart from the ground floor. You couldn't sleep on the first floor or the second floor of the home, and but everybody in hotels, because they were afraid of this gas. So we're trying to support also public authorities providing data about the environment. This is a more recent work that we are doing now, and will probably be published later on this year, on image enhancement. Now, I said before that acoustic model that is to be used because optical model generally do not work very well in water. Well, the fact is that also visual doesn't work very well because very often the visibility is very limited. I mean, the worst case is just a few centimeters, 10, 20 meters, that's very bad. If you're lucky, 10 meters, 50 meters, but you cannot really see 100 meters. And you have the so-called underwater fog. So the red channel is absorbed immediately. When you know light is the sum of different wavelengths in the electromagnetic spectrum. The red component is the one that is absorbed in the very first few centimeters of water. So you don't see any red in the water because the red channel is appearing. If you turn on the lights, it doesn't really help much. Actually, sometimes it's even better not to have the lights on, depending on how deep you are. If you're too deep, you need lights. I was in the North Sea around 30 meters. It was better often without lights. Because as soon as you turn on the lights, what happens is a phenomenon called marine snow. So it's not really snowing, but the sea is actually full of stuff. It's not pure distilled water. So all these particles that are traveling in the water, as soon as you turn the lights on, they all got expanded in our image. So they're all white points that are traveling. So this is what we call it marine snow, because in an image with lights on, it looks like it's snowing. So this work is to try to enhance images, enhance the color of the images. So from one side is to recover the channel, the other side is to remove this fog that is there, for the marine snow lights. And my PhD student now is working on this in particular to make it in a white box. There is quite a lot of work at radio image enhancement, but most of this work is pretty much done in a black box kind of deep convolutional network, and we don't really know much what's happening here, and we don't really know much on how to evaluate the sound. Because say, well, this image looks better than this other, but it is very hard to actually properly evaluate it. But he's working on trying to make this very stable. So using reinforcement learning, so that the user really understand why this color has been changed for this reason. Now this may be a kind of a process more for humans than for robots. So I'm not sure that's not the case. Of course, for humans it's nice to see images enhanced in the water. But also robots, if you use visual for navigation, we look for features, we look for things. So having a better image may also help us to understand these features better. So this work at the moment is mostly on image processing, but the second step would be to use this inside our system. So it can be underwater, but it can also be in PSV, the cameras, that is mounted to the Now, through the sonar, sonar is what I call the noisy bad brother of LiDARs. So LiDAR is light, so you get a very precise point out, more or less. Well, you don't get it precise where the light cross the window, for example. In that case, you get a little bit more precise because the light is stopped. Otherwise, it's very precise. Sonar is the opposite. I mean, it's based on a single principle. Instead of light, it's an acoustic wave, but we send a wave and we get the result. And then based on time of flight, we calculate the distance. Now, these are typical sonar images. Now, this is side scan sonar. So, side scan, you have an acoustic wave on the right side of the robot, on the left side of the robot. You can mount a side scan also on the board, you can mount it water bubbles, and then the image gets accumulated once time is passed. The vehicle is moving, and it gets one line over the accumulated image. And here is trying to understand the potential object of interest in the seabed. And of course, the seabed is not just a nice flat area, because you can have different changes. You have a relatively flat area, you have some ripples, you have different rocks, so it's different strategy. What we see here is forward-looking sonar. So we work with the Bluetooth, with the Beacon or the MB2250 that has two different frequency bands. And this is the SY image, and this is the same image in polar coordinates, transferred to the sensor, of an area in the north of Scotland in Fort William that has a big contour going into the sea. So what we see here, so this is a pillar of a big contour going into the sea. So it can be a pillar of a bridge, for example. Now, in our case, it was a station that was inside the lake where they were doing ROV training and offshore diving courses. For that, you need to be in the lake. So this is why they built this kind of bridge. And we were looking to get all these pillars. And of course, when you look at pillars, instead of looking at the seabed, if you look with the forward-looking sonar, instead of looking for side-scan sonar, the geometry is different. The expectations are different of your data. Changes in orientation may change how the image of things. So we are doing different analysis image to produce the better algorithm in order to properly detect pillars. And here we went to a multi-vehicle domain using acoustic, and this is a classical either MCM mission, non-controversial mission, or a classical, let's say, search and rescue, or what we have here, we have multiple vehicles that are coordinately exploring the seabed and finding objects of interest. Now, we use the same architecture for an archaeology project, for example. So, in an archaeology project, we are looking for ships or interesting aspects. In the first project, we are looking for mines. So what happens? We have different vehicles and the different capabilities of these vehicles. So they were coordinating by themselves on which tasks each of them should do. So it's not that it was scripted. Let's say, okay, vehicle A needs to dive and needs to move clearly forward, but they were coordinating with each other and say, oh, I can do a general inspection. I'll just do a kind of a video on board. And then you have the sensor data processing on board. You detect a potential object of interest. You have LDA localization in the water. You do some maps based on your sensor. Say, okay, maybe around this area there is something of interest. So you call a second vehicle to go there and make a closer inspection. And with a closer inspection, we have a spiral around. So we do a spiral for two reasons. One, we want to have different ranges, and the second, we want to have different orientations. So moving around a spiral was a very good way to gather a lot of information about the potential threat, potential object of interest. And then in case those vehicles was identified, sorry, in case those objects was identified as a potential threat, a potential object of recovery, you would call it your vehicle that would take care of this. So in our case, it was called a kind of a spotter vehicle. We were just launching a weight to make the mine exploding. If you're working on an archaeology project, don't do that, because you're going to destroy the artifacts. So we just go there with nice robotic armor, a good control strategy to gently lift it and take it to better place. Don't destroy it. I've seen the Titanic video where all the robots were in. I thought they really blended when they show us all the damage that they have. There's a writer with the cable, and then the cable was tangled, and they made quite a really good mess. Good. So this is Scotland in your parents, so it is real life, and this is a simulation, as you can see, that is kind of spiral trajectory. along this interesting picture. This is the green that is another low border, and then from the low border you see some object of interest, the same blue vehicle, as you can see the other one here, that's the inspection, and then we remind this is an object of interest, so it says the red vehicle, and the next steps based on the application. We also use data from that we get from sonar, from vision, to help in the organization of the robot itself. Now here are some images from Aberdeen. Working on the time was called PAVE, Prototype Autonomous Inspection Vehicle. Then after PAVE, they changed completely the vehicle, they built a new vehicle, and it was called AIV, so they moved the P as a prototype. And then it became operational for BP and Chevron, and we quite a lot of field work for BP inspection of pipelines, breakers, valves, starting, and so on. So we started this work 15 years ago, and still doing one quite strongly. Now, I'm not talking too much about organization. I gave a talk in Rome about organization, so it's better to continue with other topics. Now, the fourth aspect. Now, this is the image on the right. What I say about the logical aspects of how to do this. So, what we are interested in the high level mission. We are interested in the robot to do this task. We are not much interested in how the robot does it. Now that is why we want to decouple the high-level task to the actual implementation of the task. Because if in your implementation something was wrong, it might not mean that your task is not accomplishable. It might mean that your specific implementation couldn't work for some reasons, and we have to change it. So in this case, for example, if you want to do some inspection of an object, we can use the forward processor. In the vehicle we have two forward thrusters, two vertical, two lateral. So if you have a computer shaped vehicle, of course, moving forward is quite fast. So then a fast inspection to moving inspection. Now, if your thruster breaks, you cannot move the two lateral thrusters forward. So you cannot do the fast inspection. You cannot move faster anymore. But it doesn't mean that your mission cannot be accomplished. If you are interested in the inspect object, you are not interested in necessarily the fast inspection, you are interested in this. If this one becomes unavailable, because this, essentially this one becomes unavailable, and that's what this one becomes, actually this one becomes unavailable, and then we have to make this one unavailable in option, and so on. So we would have to see here that even if some of the components fails, and some of these fails, some of the high-level codes can still be reached navigating the graph into a different way. And this is the work that we did. We started to do, and we want to continue doing expanding this on how to arrive to a general solution on how to use faults. So on the left-hand side, we have a low-level fault detection and fault mitigation. So in this case, we just mentioned the difference, for example, between the expected location of the robot and the set location of the robot with DBL. So if you're going straight and your DBL is your compass is telling you that you are going banana, but you gain the compass to go straight, well, maybe something is wrong, either the motor or the sensors. And then you try to detect why it is. On this level, it is more high level on if I know that something is not working, I can still see how to accomplish the higher mission without using the component. And it's the same as we do as humans. So now, if our leg is hurting, then we start working in a slightly different way. Or if it can't work anymore, but it's really important to get out, so there's a fire, and we will crawl on the floor, and then lifting our legs. So we will crawl and we will get out. So that means we know that we can get out in different ways. The preferred way is using the legs, but if the legs becomes unavailable for whatever reason, I can still try to crawl and still accomplish my mission. Now this is extremely important, especially in the water, because if you lose your vehicle at a random point, the chances to recover are relatively small because the ocean is big. There's something I always tell my students, it's not a pool, it's not a small pool that you just play around, but it's actually big. So if you have a failure with your different fingers, so for example, that can tell you where the rock is, chances are that you are lost this. Well, if the robot can be smarter, and at least can find a way to reach a recovery area, or it senses it's impacting water, so it tries to go up and try to connect to Wi-Fi or GPS or radio satellite or something. So then we have a little bit of more smart mechanism for the robot to increase its success on accomplishing a mission and extending its life expectancy. We all want to live longer, let's also get our robots to live longer. Now, when we look about sport management, the question is how do you test it? I mean, you don't want to break the robots all the time to test it. I mean, you do a lot of testing all the time. That wouldn't be very practical. So what we test is in general you simulate a failure. So you kind of sneak in and we intercept the command to the cluster and you give half of the command, 50% or 30% or 0% if you want to simulate a complete failure of one cluster. But actually, the interesting things that happened to us was that one of the clusters actually did break during our field activity. So it's something this unsympathetic process we didn't expect, we didn't even realize. We realized at some point in the robot became really strange. So we were commenting with the nothing going forward, but when we were really going forward, and we didn't understand what happened. It was about almost the one last day. Then we came back to the lab, and then once we come back to the lab, we have all these aspects of cleaning up your robot and sorting everything here. It was very salt water also, so it's very important to properly wash things with salt water because it's very deadly to process and so on. And we're looking at things, and this is there is a cap that we removed. So looking at the cap and the lens, for safety, because otherwise this would be very bad. So it's a cap. So we do something strange, and then we open up and we saw that actually two blades were broken. Now the interesting thing is that we did have our software running, at least in passive mode, and our software was doing that. So usually what you have your control laws, you have your trust allocation, you have your linearization, and then you give a commands to the processor. Now in our cluster diagnosis, we had a fault detection module that was looking at energy readings, and then if a fault was detected, was trying to ramp up our cluster allocation mechanism. So how is that? Think about this is the vehicle in healthy conditions. So you want to go straight, you give more or less the same power to the left and to the right cluster. I always say more or less because we are not in a mathematical representation where it's exactly the same value. Real life will never be the same value because the two clusters will definitely be mounted slightly different to each other. We are not very perfectly the right coordinates. Not all the two clusters would have the same force torque parameters, even though they're kind of the same factory and so on. So it would be almost the same forces that we give. Now, if this one starts to behave weirdly, so you give a certain command, but then the motor is not able to execute it. What happened here is that the robot will start to rotate. Now we have used the lateral cluster to balance this rotation. So in this case, we do a full mitigation of the lower level where no plan is touched, no mission is touched. It's just an adaptation of the component base. So what happens here is that we detect a fault, we redo our transfer allocation matrix, and therefore we continue our operations with the different operations. So that's the surge movement, so moving in the direction of the vehicle, is not mapped only between these two clusters, but it's mapped between these four different clusters. As here it's the plot from the time where the cluster was broken. When in the lab we were looking at all the logs, And you will actually see that the real consumption of energy was much lower than the expected one. And why is that? Well, if the thruster is broken, it just moves empty. So it doesn't push the water out, so it consumes much less. So this was very interesting because we weren't planning to detect it. And it was actually interesting to see actually this worker would actually work in the field. But here are some videos of different projects that we've been involved in. So this one is already more than 10 years ago at the center in Italy, in Francesco. We are participating in the Marine Robotics competition, and one of the tasks was autonomous inspection of the wall with no prior information about the wall. So the robot in this case is seeing the wall through forward-looking sonar, and based on the forward-looking sonar, with no information about the map, can automatically adjust its orientation, its precision, its movements, in order to be the same distance from the wall. On the top left, is a computer simulation, which was in the North Sea, we cannot really get good footage. But our lab in Edinburgh made the world record of autonomous pipeline following the North Sea. And this was also done in the this one comes from the Pandora project. It was a big European funded project which we coordinated when I was in Edinburgh. And the University of Girona made key contributions here, so they're using their assets in Girona. At the same time, we have King's College working on the planning aspects, and we have the Italian Institute of Technology, which is IEEE as well. They're always working on machine learning aspects. So this is about getting to a tunnel and having a valve. At the same time, understanding if a valve is stuck, don't overkey it because you break it, and there are accidents happening in the field where big ROVs piloted by humans because force feedback, they just broke valves because the valve was stuck and it was just pushing the feedback. So here is a completely autonomous, so looking at the configuration of the panel, the valves, looking at the goal, and planning the joint control of the arm and the vehicle body. And this is interesting because you cannot do only single control. Because as soon as your arm moves, your center of mass moves, and then you screw up. So if the arm does anything, you always need to comply to compensate with your other process on the vehicle side. And this one was a previous Marine Robotics competition, where we were the only team who managed to get it in the box. We didn't manage to exit, that's a problem. No, actually, we did exit when we did the test. So in the test, we were the only one who managed to find the box and enter and exit. And but the test that we were doing during the test, we were monitoring the cable. Then we remove the cable and we readjust some of the parameters. And what happened is that the cable was really heavy. Without the cable, even properly adjusted, the vehicle was slightly too high, and the antenna got stuck on the box. We did get the points from getting inside, we were the only team who managed, but I'm still a little bit sad that we didn't manage to get out, and there was no way to get in touch with the robot, because there was no communication, no cable, no models, nothing. So we had to set it out. Some of the activities that we do in our university are not only in the maritime domain, but Christina, for example, is doing activity on human-robot interaction. So first, she was trying to understand what kind of behaviors are prone for humans to consider a robot having itself. So at which moment I consider this as an object, or I consider this as an its own self. So the idea is that we do not define what is a self, We don't enter into the definition of the self. Now we enter into what people perceive as the self. So it's a very philosophical, psychological project. And then it evolved into behaviors of robotic behavior which are more friendly to humans than others. And we evaluated different speed, different noise, different approaches. You prefer that the robot comes towards you from the back, from the front, from the side, how close you want it. And therefore we developed now developed a nice structure with different layers. So if you see a human, then your behavior will be different around the human than if there is no human. So what I like to say is it's a kind of policeman syndrome. So if you are on a bike carrying a red light, there is no traffic whatsoever in the countryside, you just go on the bike, there is no one there. If there is a police car, you actually say, well, maybe I shouldn't cross the red. Or you cross the green, but you shouldn't. If you see other people around, okay, then you will take the sides of the sidewalk. So in a similar way, other robots can adapt. So can be really more efficient and on different efficient on its goal. But then when it's a human being, then it changes behavior. So this is a part of different behavior that we explored, and then we have different human participants to give us some feedback from our students, but also online. If you want to get any specific demographic, you go to one of the portals, we select 100 people of this religion, of that college, of this age, of this gender, and we can get something like that. Great. And I want to finish then with a couple of words about studying in Germany for you. If any of you is interested, no, there is one more slide for somebody in education. Introducing robotics on a bachelor level, and we would like to also have an IEEE student level. I'm pushing my students to try to do it. And then I can be an OES level, that we can launch joint activities, for example, or a RAS level, or general IEEE. This is what we can do. Now, studying Germany. Well, first of all, there is a lot of interest from India to come to Germany, and the interest is increasing a lot recently. Also because in the US the situation is what it is. UK, the situation is what it is, and a little slightly better than the US, but still, having this economic easy, and you get kicked out of the country even after you finish your degree, unless you offer this day, out of the European Union with Mexico. So there is more and more interest about Germany. And of course, you may ask, yeah, okay, Germany is great, but what about language? And that can be an issue, but not necessarily. So at bachelor level, our university does all programs in English, bachelor, master, PhD. Other universities have started. So there are a few others, public universities in Germany that started also to offer the English-speaking courses. To go to master level, way more universities in Germany are offering English-speaking masters. Now, depending on your future, if you see yourself that you want to be in Germany, I would still recommend you to that. Which I didn't. I'm speaking with German, but I'm not super fluent. But if you really want to work with the industry there, and they don't like to speak with you in English, I mean, it's the same, people come here, yeah, you are in IIT, it's fine, and you are happy to speak with you in English, but then you also want to speak your regular speaking English. In the industry, it's the same, so it is way more complicated. There are big companies in Germany, you will have people that you can survive in English only. But if you get there, it's useful to study if you want to study. Now, why Germany? Why am I in Germany? Well, in my case, it's not that I say that I picked Germany. In my case, I picked the country where I could have interesting things to do. My view is we live only once, So if I don't get up in the morning eager to do what I do, it means I'm going to change my job. It's simple. And why do I need to waste my time? And in this case, they don't do Germany, but I've been in different places. And I have an interesting things to work at else. Oh. Okay, so the text is not coming. But Germany is the powerhouse of Europe. So in terms of economic growth, in terms of population, in terms of industrialization, Germany is really the big country in Europe and now, I have to be completely honest. It doesn't mean that everything is perfect. Digitalization in Germany is not happening the way it should happen. It's one of the battles I have also with my current administration in the university. Say, oh, you need to pass your signature to this form. Okay, I sent that email, it's fine. I don't need the signature. No, you need to sign this. So there is some aspect of digitalization which I'm still struggling with. But overall, Germany is a country with many opportunities. Now, the bachelor is 3 years, master is 2 years, and PhD is variable. In Europe, often we try to finish PhD in 3 years, but it's mostly what we say that what happens. In Germany, in particular, the median age of finishing PhD is 5, 6 years. Sometimes it takes time. But that is also because sometimes PhD students are considered scientists as well. So in many cases, they are not considered students. They do receive a salary, so for them it's a job which actually being there. Then at the end of the day, why do you really need something that can be a contribution to get a PhD, otherwise you are a researcher in the London. Now for the requirements, of course different universities have different admission requirements. So in our university, for bachelor level, we ask SAT, and it needs to be greater than a certain number, which is another now. We ask English proof, because everything is English. That can be pretty much anything that we can ask, or even the legal certificates. We have a recommendation letter, and so on. And application for master is the same, but we don't have an FIT requirements for master. Then there are requirements from the state. You want to come to Germany, and then the state is kind of telling you, okay, how are you going to live? How are you going to survive in Germany? Can you tell me that you have enough means to survive? Or you get accepted to the university, you travel, and then you are on the street because you don't know where to live, you don't know how to get food and everything. So you need to show, in many cases, a block account that has at least 12 times something like 1,200 euros per month for 1 year. And then from this block account, every month you can take this money out. But they will not give you the visa unless you have a full scholarship that pays for everything. If you don't have this block account. And the block account allows you to withdraw money on a monthly basis. PhD students usually have a stipend or an employment, depending if you place a stipend or employment. So in that case, it is enough. I had a problem once that the student wanted to bring also his wife, but he didn't tell me. And the amount of the scholarship was not considered enough for 2 million. For employment, the usually is no problem. Mine, but for a stipend, usually it is considered enough for one person, but not for two. PhD programs in Germany are very decentralized. So, I'm Italian. In Italy, you have PhD cycles. So, one PhD is to start in September, there is a certain length, and after that, you can get one extension, otherwise, after that, you're out. In Germany, everything is decided by the PhD supervisor. That's, I mean, not everything, of course, the school decisions and the very standard and everything, but in general, the PhD supervisor is the one that decides if the person wants to come. One aspect that we need to take into consideration from India is that I've been told that in general, we require 1 more year of university because the first year of university is considered in Germany the last year of high school. So that's why 3 plus 2 might not be enough. It should be like 4 plus 2 in order to start PhD. But if there are exceptional cases, we can even accept a PhD student from master. That is not the normal, so it's not the usual route every master student apply. So we can have, there is a committee, and the requirement needs to be among the top in the class. With already some research experience, is to have either a paper or a scientific writing that has been produced, and we also have to do an exam. Where the PhD supervisor is not even there, just to make sure that it's independent. So it is possible to jump on PhD and from bachelor, but it's not big common. So, now, one thing for information, DLD has many different products that can support mobilities. So I have a student from India, as I said before, from CSIR, Silvi Pilani, that she came with a sandwich PhD. She funded PhD in Pilani, she came to us for 1 year. She offered an extension for the 2nd year. Now she's back in Pilani, and next year she should submit the thesis. I'll see if I can come for the thesis defense. Otherwise, DLD does also provide information about studying in Germany. And, from the DLD website, you can even go to the Study in Germany website directly. And this also provides you lots of different tips on now this is relatively recent. It's from April this year, so just a few months ago. So it seems that Germany is becoming more and more popular for India. So if you think about China and India are having a little bit of political struggle from time to time. The US is a political struggle with everybody. Today, you don't know where they are, depending on the government of today. Now, Germany is, and the European Union is at the moment a kind of a stable place and very human-centered. We try to care about the good balance. Okay, don't look at me about balance between work and life, and I work 20 hours a day. In general, we look at about these things. And on the Study in Germany website, there are also a specific pattern that are looking at on the requirements to study in Germany. Great, and then we arrive to the end of our talk, and I'm pleased to be here for your questions. Thank you.
The questions from students. You can ask about the question.
I can ask one question. If they're going for undergrad or master's or PhD, do they need to pay tuition fee or?
Good question. So, my university is a private university, so we do charge fees to the universities from the state. The fee is chargeable for bachelor and master, but not at the moment not for PhD. Now, from the fee aspect, we also have different products as these scholarships. Not every student gets scholarship, but we do have several different scholarships. So we have the alumni scholarship, for example, that our alumni gives a 1 full scholarship, undergraduate and 1 full scholarship graduates. We have merit-based scholarships, and we also have a program that is tuition refundable. So that's I am one of the students now. I managed to get 50% discount So from the fees, and the remaining 50%, he doesn't have to pay anything now. It's only, will only pay later on as a percentage of the salary. So in case you don't find a job, then you don't have to pay anything. So I kind of like the idea. So if you do a shitty job in education, then you don't have to pay us. If you do a good job in a multi-millionaire, then you need to pay a little bit more than the standard fees are charging. It's a fixed percentage of your salary because we don't want to get into the interest aspects because culturally, some part of the population would why doesn't like interest. So finding a way to balance is just a fixed percentage of the salary for a certain amount of years. And I was meeting with some alumni and I was asking about the program, if it was working for them or not, because I was also afraid that it was getting a little bit in the depth after. I, in general, don't like that. I wasn't too happy about this in general. And they were telling me that they found this very good. So I met alumni in Rwanda, in East Africa, and they said, we finished our master they had a job in Germany, and then they were paying a little bit money. They said, if we wouldn't have the possibility to defend the solution, we wouldn't have the chance to actually come to Germany. Then they came back to Rwanda because they got an offer. There was a much higher offer from a position, but a lower salary. The salary is different, and it was fine. She just communicated the new salary to the company, the new contractor, and then the monthly payment just dropped because the salary dropped in Rwanda, even though the position was higher. So the feedback that I received was very positive about it. For PhD, there are some people who are thinking about charging fees, but not yet. So take a chance before we start.
Do you have any plans to make the robots sustainable?
What do you mean by sustainable?
Because would be a use of carbon waste because
Okay. Yeah. Yes. That's a very good question. Now, we even did, especially from a journal of sustainability, the contributions were very good, of course, especially if you are an author and you're looking very good contributions. But at the same time, we didn't really have anything that was much on harnessing energy in a different way or materials from the material perspective, biodegradable material perspective. It's an interesting topic. It goes a little bit out of my expertise, thinking about energy batteries. What I can think of is how we can change the plant, how can the robot change the plant to be more efficient in the energy consumption. That yes. So that is something that we did also with the thesis with the students. We said you want to inspect these 3 points in the sea. These are the carpets. Do a pattern which is the optimal pattern, not only in terms of length of the pattern, but in terms of also the energy that you need if you consider the currents. If you consider kites, the currents are even changes in the day with the electron. So in that case, we can figure out how to use AI-based planning in order to be more sustainable.
I don't know. Like you were showing from this slide, there is 5 parts in the application. So there is a non part.
Yeah, so it was a multi-vehicle coordination. So we had one vehicle that was doing a longboard on the water. With the idea to inspect an area. If you need to find objects of interest in the area, the standard way is to put a longboard on it. You can also do a different path, but the longboard is kind of easy to program. Also, in the programming of the longboard, you can be efficient. So you can decide if you do the long transit, making the pilot and so on. Now, when you do the longboard, you gather data in the first time, and you also process the data. You have a machine learning module that's trying to detect potential objects. Now, if you detect something that may be of interest, you send a second robot. That is, the second robot goes to the coordinates sent by the first robot and does the spiral around. And the turnaround is done in order to discriminate between the real targets and the false positives. Because sometimes a rocker can be very similar to a mine, and in the end, acoustic is high intensity and shallow. So it's important to go there a little bit closer and to really see if there is really a lot of interest. And then this one, if it was determined that this was an object of interest, then it was communicating the coordinates to the third vehicle that we call the disposal vehicle. It's going there, and in our case, going there, but the operation can take about 3 minutes. Yes, the deadline is
later class where we should do what we continue wants mentioned that as we have known system of gravity is moved. So all of that control strategies we adopt deal with changes in mass and magic pretty large changes in mass and tremendous effects of that.
That is something that we have to consider in our coding. Now, if you have a single vehicle, a PID controller was pretty okay, because the water is a pretty low mass filter, all the high frequencies are taken care of. So even just a D controller is fine. In that case, no, we have to use something else, but the group from Greece was one from the controller, so we have to refer to the paper from that.
How did you identify that autonomous smartphone? Was there some other sensor?
How we identified that the cluster was not working. So we had we placed in the robots energy reads, current reads, and each cluster. And we did a model. So if we get the vehicle to move forward, what are the reads from the different currents and between each cluster. Now, if the cluster was broken, that means it wasn't pushing the water out. So it was just moving idle. So it was consuming much less energy. So there was much less current that was passing. So there was a discrepancy between the model of the consumption of energy consumption and the actual energy consumption. Because we had 6 clusters, so we placed 6 current reads at each of the clusters. So that was fine. Then we did the second work. We didn't want to have all this hardware involved. In the second work, we only considered the difference between the expected trajectory and the trajectory given by the DDL. By DDL plus compass. So that reckoning. So if you tell the robot to go straight, that is 90% of the lawnmower is straight. And if your sensors are telling you that you are moving, then you don't even need the current sensors, but you can already tell something is wrong because you are you see a behavior that is different from what you always expected. But be careful that it doesn't mean that the study that the process is broken. I mean, in most cases that is the case. But it can also be that the sensor is broken, the idea is broken, or the compass is broken. So, actually, big currents can also be seen as sports. So, I mean, it doesn't have to be yourself. It doesn't be static. Yeah. That's a good point. It can also be your part, nothing wrong with you. But see, even nothing wrong with you, you still need to adapt it. So if the word is wrong, then you can still adapt it. So fine.
So the current sensor even might have some, the current sensor, it might also have
Yeah.
Then you can't actually correct that over.
Well, everything can be broken. Because, well, the next step would be yes. So, in order to determine what is broken, you would try to do specific tests. And you say, okay, I stop my mission and say, now I will just go forward. I'll try to exercise one process at a time. and try to see if I get the expected answer. But then you can also say, yeah, maybe the software develops as a bug. I mean, at some point you have to stop.
I request Mr. Francesco to verificate our speaker.
What's the question?
Yeah. Thank you.
So now I request Mr. Dinesh, I will give you his student step to post the order.
Thank you, sir. On behalf of IEEE student chapter 5 members and IEEE class section, we are thanking you to provide this insightful lecture. I hope the participants both in online as well as in person have benefited from your talk on technical aspects as well as how to reach Germany for their future studies. I hope it will be useful for us. Thank you so much for coming.
Thank you. Thank you. So I call anybody to say
Now we'll be sure to do
Yes.
Yes.
So I think